And we are live. Good evening and welcome to the PM podcast. Thank you for joining us. I am M. Marco here with P. Farsa, and we have a
Don't do that. I don't.
very
That's not gonna
special
be a
guest
thing.
with us this evening, our
T.
friend Tristan. Yeah, T. And
Yeah.
T is here to teach us about the creation of the universe. So if you want to introduce yourself, Tristan?
Yeah, I just wanted to. Hello, by the way. I am T. I wanted to give a little disclaimer. I am approaching this subject, very vast and complicated subject, with the background of a late stage bachelor degree. So for any kind of more specific knowledge relating to what we're going to cover, I would refer to actual astronomer for that. This is going to be very basic intro to evolution of the universe, what happened around the time of the Big Bang, consequences that come from there that led to the universe we have today.
Okay, so take it away, Tristan.
Okay, so I wanted to first present the model that encompasses our current understanding of the universe, which the Big Bang theory is a part of. So this is the lambda CDM model. I'll go over what this is an acronym, so I'll go over what each of those letters mean. So first off, we have the Greek letter lambda. So this represents the effect that dark energy has on our universe. It's the driving force of expansion. So I'll go a little more into detail of when dark energy actually comes into play and what it is. After that, we have CDM, so that's cold dark matter. It's important to mention that the cold comes from the fact that it is a lot smaller than the speed of light. So dark matter, I'll also go in a little more into
Wait,
detail.
hold on. It's smaller than the speed of light?
Like the rate at which the matter moves around is smaller than the speed of light. Like way smaller. Like
How
when we
fast
say
is it moving?
the speed at which it's very negligible compared to the speed of light. And we have like a distinction for this because there was also a theory that was posited. I'm talking about something that's called warm dark matter, which was another idea. The main difference between the two is that if we had a universe that was composed of warm dark matter instead of cold dark matter,
Mm-hmm.
things would break. Like it would be a top-down type of universe where the first things to form would have been these cluster super clusters and galaxies and then stars and then everything
And
would
then
break
we would have
down
had like
instead
atoms
of
and stuff.
having, yeah, exactly, instead of everything coming from like a bottom up type of sequence.
Yeah, okay, so clearly that's bullshit.
Yeah, so warm
Dark
like but this is all like still very recent. Like warm dark matter, it was proposed in 1982 and it was only ruled out until like the 1990s.
Okay. Okay.
So when it
Because
comes to like cold dark matter, do we have more? Is it still just a theory? Is it just hasn't been ruled out? Like there's no way to like actually
so the
disprove or
thing
prove it.
about dark matter is that you can't. The idea we have about dark matter is that it's matter that doesn't interact with, the regular matter we have around us. Hence why we say dark. It has nothing to do with like the color or whatever. It's kind of like a more maybe precise denotation of this would be transparent matter, because we can't see it except for its gravitational effect in the universe.
Mm.
So there's a few ways to kind of like figure out that dark matter exists. I was gonna go a little more into that like later on,
Okay.
but for now, all you have to know is that this lambda CDM model is the encompassing model that astronomers and cosmologists rely on to explain how our universe evolves and the laws of physics that are found within. Make sense?
Yes.
Understood.
Okay. So so now the main topic of the conversation, which is going to be the Big Bang and what comes after that.
That's why I called last night with your mom. Sorry. All right. Continue, please.
That's I tried calling her, she wasn't answering. I must have known. He was with M.
I'm okay.
Anyways, history of the Big Bang.
Yes.
So it was first introduced as an idea by Father Georges Lemaitre in 1927.
Mm-hmm.
So he published a paper talking about the redshifting of galaxies that are increasingly, like, he basically showed that galaxies were moving farther and farther away from us from redshifting. And now you may inquire as to what redshifting is.
Yes.
It's basically the light. Like, I mean, are you familiar with when you're looking out into space, you're looking at the past?
Yeah,
Yes,
but some
That
people in
makes
the
sense.
audience
because
might not be.
the light
So
makes your eyes.
whenever you're looking at anything in space, you're looking at the light that emanated from this object, however many light years away it is from you. So if you're looking at the sun right now using like a telescope, you're looking at it how it was 8 minutes in the past, because that's how long it takes for light to reach Earth. If you're looking at something that's 100 million light years away, it's because you're seeing it 100 million years old.
There's some things that might not even exist anymore that we're still seeing.
Yeah, 100%. There's a bunch of things. Most of the universe is going to be completely different.
Is that
Like
why
the
it's like
old,
the observable universe? Because there are things that are
That's
outside of our range of observation, because the light just
that
doesn't reach us anymore.
is a very good question, which we will approach later on.
Getting ahead
yeah,
of
no
myself.
spoilers, Pars.
Yeah. But no,
Apologies.
it's good. It's good to have these questions. I mean, this is like kind of the natural route of how you get interested in these things is by like start somewhere and then it branches off to a bunch of other topics which are really fun.
So what
So
is
this
redshifting?
So redshifting is the light that you see coming to you. Instead of whenever, like, are you familiar with like emission spectra? So like light has a emission spectrum. So visible light comes in like a bunch of different colors.
Okay.
Mm-hmm.
So basically, like visible light includes like anything that's like red, blue, green, yada yada yada. On the bottom end of this visible light spectrum, which is normally like in nanometers, you're looking at the wavelength of light coming from an object. And based off this wavelength, you should see an emission spectrum that's going to encompass all the colors. But the further and further away you are from an object, as like we know that space is expanding, right? So because space is expanding, the light that is coming to you from that object, from the initial location, it's actually also trying to travel through space as space is expanding at the same time.
Holy crap.
So this light gets stretched out. This light
Yeah.
wave gets kind of stretched out, and is why we say that it's redshifted, because now it tends towards a longer wavelength, and the longest wavelength you can get of visible light is going to be a red like wavelength. So he did this by looking at the Doppler effect, which is basically what this is. So the Doppler effect basically tells you that if something is approaching you, let's say you have an ambulance, right?
Yeah.
And you hear the ambulance's siren. And then if you're stationary with the ambulance, so you're not moving, the ambulance is not moving, you hear it blaring like, alarm.
Yeah.
But if the ambulance is moving towards you, it gets increasingly and increasingly louder, even though it's ringing at the same frequency. And that's because as the sound waves approach each other as the ambulance is moving in space, they constructively interfere and grow larger. So your perceived impression of this like sound is a lot bigger than the actual initial frequency that is being emitted.
Right.
So,
So
like example, an ambulance that is blaring out at 100 decibels is at the faster and faster it's moving towards you, the more it's going to increase. So it could be blaring out at 120, 140 decibels is your perceived like impression of the sound. And then the opposite is true when you're receding away. So when you're receding away, the ambulance actually sounds less and less loud than the initial frequency that it is emitting.
Okay, this might be a dumb question.
No, I don't believe in them.
We were talking about redshifting and light, and you compared it to the Doppler effect, which is about sound. Does that mean that sound and light have similar properties?
They're both waves. So that's all you have to. The only thing you really have to.
Yeah, you're right.
They're both. Yeah, that's literally it. It's if you can picture sound waves building up and interfering constructively, or kind of like stretching out and being destructively interfering, then you can picture light. The wave of light is getting morphed, and we're perceiving the light stretched out.
Right.
As something is moving farther and farther away from us. If something is moving towards us, we're going to see it on the opposite side of the spectrum. So the two borders of the spectrum, you have blue, and then it's going to go into green and yellow and orange. Or sorry, blue and then purple and then green and yellow, orange, red,
Yeah.
something like that. So if something that's moving farther away from us is redshifted, what would the color be of something moving towards us?
Blue.
Exactly. So anything that's blue shifted, it means that it's traveling towards us. Typically, this means that it's being pulled by gravity by some object. And the light we see is actually blue shifted because it's shortened now.
Okay, I see. And so
Because the
no,
light that was initially sent actually has to traverse a shorter path than it did originally. So it literally like changes its shape.
what do you mean the light that was originally sent?
Like let's say you're observing a planet that's like 100 meters away, but then as the light you're observing from that point that was sent from that planet, let's say at like time 0,
Yeah.
time 10 like let's say it would take 10 seconds for it to reach Earth if it wasn't moving, then you would observe like a full spectrum. But if the planet is moving towards us and now the light actually takes like
Yes.
6 seconds to traverse,
Then it would be
there's a
blue shift.
relationship between the amount of time it takes for light to get to us and it's like blue shift or red shift.
I understand.
Right.
I understand. But so
That's like this is also the premise for how we can tell the distances of galaxies and stars. It all comes from this like concept.
you look at kind of what spectrum the light is on there.
Exactly.
Okay. And so because of the red shifting, that's how Father George was able to tell that
Father Lemaitre.
Father Lemaitre, let me show some respect. So that's how he was able to tell that galaxies are like expanding away from each other, right?
Yeah, exactly. He was the first to kind of like show this mathematically.
So was
And
there
he
ideas
said
before?
the idea, like the prevailing idea, was that we lived in like a static universe.
I see. Yes. Yeah. I mean, which is
So
like intrinsically that makes sense, right?
yeah, I mean, if you don't believe, like, if you can't, it's hard to conceive of the universe as being anything but infinite. There was also a kind of obsession that mathematicians and physicists had back then with finding the beauty in nature through math. And a universe that is just infinite is more beautiful and more like mathematically sound than a universe that has all these weird fluctuations and Big Bang and origin and expansion. This all is counterintuitive to what beautiful nature should be.
That is a fascinating argument. I never thought
Yeah,
of that. Would you say that mathematicians and scientists today are cured of this obsession?
I would say that there is still there is like for sure still that hope or that like I feel like physicists try to guide their experiments and their theories based off of the idea that we're getting closer to this like beautiful, perfect, like well-defined construct of the universe. There is a way, there's something we don't understand, there's something we're missing to make it more simple and more well understood that doesn't take like enormous amounts of computation. Like all the math that should explain the laws of the universe should be very, very simple. We just haven't gone there yet. That's kind of the idea.
I see. Okay.
So
How did he go
yes,
from, because you can believe the universe is expanding, that
yes.
doesn't instantly tell you about the Big Bang, right? So how did he go
No.
from point A to point B?
So I if I'm not mistaken, he believed that because the universe is expanding, this is like kind of the first showing of it, then there must have been some sort of origin to the universe, and there must be just kind of like the end of the universe is kind of like I don't know what he believes specifically on that, but if it is expanding, it means that if you trace it back in time far enough, there should be an initial state, an initial point, right?
Right. Yeah, it wouldn't start at like half its size. That wouldn't
Yeah,
make sense.
like it just kind of makes sense. Like you see a kid, for example, like grows up, like you would assume that like they came from like they started off really small.
Yeah,
Like things
sperm.
don't just kind of like if something especially is still expanding, you would assume that that there was an origin for this croissance, right?
Okay, so he just extrapolated like, okay, logically, if the universe is in expansion right now and still going, then if we backtrace it, at some point it was minuscule.
Yeah, and a lot of physicists were really upset about that, especially the atheists. Um, they were upset that like now you have this religious dogma of like Genesis that is confounded with like astronomy and the laws of the universe and physics and in general.
So what did the atheists believe then? That there
They
wasn't
wanted
a
to
beginning to
find
the universe?
ways, like Albert Einstein was literally so another point to talk about the lambda that I mentioned at the beginning. So
Yeah.
I mentioned that it was the expansion rate of the universe. It's related to dark energy, and like that's what we know it as today in our model. But the term actually comes from Einstein back when he was trying to find. He was basically trying to fit his calculations for general relativity to fit a static universe. And he wasn't able to do that unless he added this kind of like arbitrary constant, which he called lambda, which is the cosmological constant of the universe, which made it so that his calculations worked for a static universe. And this is what he believed for like a really long time. So he's the one that came up with the idea of lambda. And then once he was convinced finally that the universe actually came from something and there was this Big Bang and it wasn't a static universe that we lived in, he discounted it from his equations. And only later on was it repurposed as lambda talking about dark energy.
So because at first he didn't believe the universe was actually expanding, for his formulas to make sense, he just had to plug in this bullshit variable?
Pretty much. Yeah, pretty much. And then everyone was
You make
happy with
your
that.
own truth.
It was
I guess so.
literally,
That's
bro,
kind of surprising considering. I
they
feel
were
like
committed. It's because the rest of his theory worked so well. Like general relativity was like groundbreaking, you know. And obviously it was like him, and it's not just Einstein. Like he built a lot of the foundation from it, and obviously worked and collaborated with many people over the years. But it's like a theory that took like a couple decades to build up to,
Jeez.
and it just fit so well for most things.
Except for this.
Back then, yeah. But now we have the lambda CDM model, which
Yeah, which
encompasses relativity as well.
I see. But I still don't understand what did they believe was the origin of the universe? Or was there an
They,
origin?
they didn't think there was origin or end. The
It just
isn't it kind
is.
of
the
isn't it kind of
universe
the
was
opposite
infinite.
like today that like I feel like most atheists would like to argue for the Big Bang in comparison to like a like a priest or a father coming up with a theory like this.
What do you mean?
I think that's a bit of a side tangent, but I feel like most atheists today would argue in favor of like the start being from the Big Bang, the beginning of the universe being the Big Bang.
Yeah,
compared
but Parsa, it's not just that the start was the Big Bang. He's saying that back then they just didn't believe there was a start.
That's crazy.
Like which I can't even conceive. Like it just
I
is,
mean,
but it didn't need to
So
start.
everything
Like it
has
just
always
was.
like everything that is has always been pretty much.
Yeah,
like,
it's like I can't even wrap my head around that.
dude, that's the most beautiful way to like see the universe. If that's the case, oh, it's so perfect. We're so.
But how did that come to be? You know what I mean? If it always has been,
I mean, I think it's just
how did
like
the bang happen?
through. I don't know. Through like the evolution of like human cognition, we just always assume that like when I think it's when we first realized during the Copernican revolution that we actually weren't the center of the universe and that the universe actually has its whole own thing going on and we don't matter. It was taken to the extreme where like the universe is like this infinite being
That's
that
reassuring.
has no beginning, no end, and we're just like a small little fragment. And I think it was kind of I think that's kind of where the idea came from,
That doesn't
generally
stress me out at
speaking.
all.
No, it shouldn't. It should
It
comfort
really
you to know
shouldn't.
that it doesn't matter. I feel like life would be way more stressful if you believe that, your life actually matters and your actions matter.
But
No,
you
no, I'm
Imagine,
serious
bro,
though. I feel like
imagine if
that's
there is a
stressful.
heaven and hell, dude. Oh my fuck.
yeah. In the grand scheme of
There
things,
might be.
your action, hey, there
Well,
might be.
well,
But in the
okay.
grand scheme of things, your actions, yeah, if you put it on the scale of the universe, your actions don't matter, your life doesn't matter compared to like the scale of it all. But
You serve zero purpose.
like
Your life is meaningless.
exactly. Like
You yourself now.
oh, on like
No, it's
We're
slow to your
sidetracking.
god.
We're sidetracking
It's slow to
super
your
hard.
god.
but like
Yes,
on a
we're
smaller
sidetracking.
level,
Barca, stop
right?
stop derailing.
I didn't derail you. Told me to kill myself.
I was telling the audience, not you.
That feels worse.
Yeah, but it doesn't matter because we live in an infinite universe.
So
No, we
your
don't.
actions and your words do not matter
Okay,
at all.
okay, back on topic.
Yes. Okay. So we have Lemaitre, 1927. This comes out. A lot of people are still upset about it because they're not convinced, right? Then in 1929, Mr. Hubble, Edwin Hubble, Edwin
The
Hubble
telescope.
is more, yes, exactly. He's more generally known for the person that
He was a
found that the
telescope.
universe was expanding. What'd you say, Parsa?
I said
Or
yes, he was
P?
a telescope. I just found it funny.
Why is this
Sorry.
guy here, by the way?
Okay.
I like having like a live audience while we record.
Yeah, honestly, it's
What
funny.
do
That's so mean. Okay, Forza, we'll let you
Back
continue
to
more.
being serious. Edwin Hubble is the one who's typically credited with finding that the universe was expanding. Like if you look it up or in textbooks, like a lot of the time, he's the one that's named for it. And it's because he presented a more convincing argument using a paper that he published in 1929 that more like accurately describes the redshifting in a mathematical way that pleased the scientific community a little better.
So, I'm sorry, what
He
year
like
was
catered?
this?
Sorry?
So what year was this?
This is 1929. This is 2 years after
Okay.
Lemaitre published his own paper.
And when would you say it became commonly accepted? Like after 1929, how long
Not
did it take to become
not until 1965.
Wow, okay. Like almost
So it took
40,
like
40 years.
a lot of what we know about astronomy today, and even like the lambda CDM model, like all these things. I don't think people realize how recently developed they are.
Yeah. No, you're
You know,
you're
like a
you're right.
lot of the things that we're figuring out, it's like in the 90s and 80s and even like 2000s is when a lot of this is like
Right.
being proven.
It's not like we know that, like, let's say the theory of evolution is pretty recent, but it's like it's not like,
Yeah,
like
yeah.
our parents were alive when the Big Bang was still being debated.
I mean, dude, there's like gravitational waves, for example, were theorized by Einstein about well, maybe not 100, but I mean like 80 years before they were proven in like 2018.
So
So it's like
he
these
just
kind
had
of,
like, I feel like this is right.
well, yeah, it's like, oh, it makes sense according to the math in our models. We don't have the tech to observe it, and then we develop the tech, and then it's like, oh shit, actually, he was right. Or it's like how black holes, they were theorized like late 1800s, early 1900s, started gaining a lot more traction. Albert Einstein himself also theorized they must exist, and they cause a lot of problems in his general relativity equations, but that's a topic for another day. Until Stephen Hawking is the one who came in and he's mainly known for his contributions to like black hole radiation, known as Hawking radiation. But he's also the one with Roger Penrose who proved that the Big Bang was indeed the thing that started the universe. And this is like in 1982, about something like 1980.
What was like, obviously you can't summarize it like in 2 words, but
They had mathematical proof that using the cosmic microwave background, so this is what happens in 1965 that kind of changes people's opinions.
yeah.
Is the discovery of this
So
cosmic microwave background,
and what
and they used
is this?
I'll get to that.
Okay.
Sorry, I feel like I'm saying that to a lot of questions, but
Yeah,
I
we
feel like
got
as I go through, we'll answer them, and if I don't cover it properly, then we can. So basically, Hubble now proves that like redshifting is going on and that galaxies are receding. And not only are they receding from us, but to also give proof of this is that he studied 46 different galaxy clusters.
Mhm.
And he noticed that most of them were receding from us. So the light coming from them was redshifted. And it would not make probabilistic sense. Like if we were in a static universe, we should have equivalent like red shifting, blue shifting, galaxies should be moving around, whatever, according to their own laws of physics. But if every single galaxy is moving farther away from us, and the further and further a galaxy is from us, they're moving at an increasing rate. All of these galaxies displayed that trend. Then it must be that space itself is expanding.
Right.
Okay.
Right. Okay.
Okay, I have another stupid question.
Again, I don't believe in them.
How can space be expanding? Okay, I think I just answered my own question, because the quantity of matter in the universe is limited, right? Rien ne se perd,
Yes.
rien ne se crée. But
Yes,
is it
exactly.
expanding because there's just more dark matter that's filling up all the space?
No. That
So how
is
can
an
it grow
important
if
distinction. Dark
we can't produce
energy,
more matter?
we can't. Dark energy and dark matter, two very different things. Because it's not the dark matter that has some sort of energy, and that's why we call it dark energy. They're two separate concepts with two very separate effects on the laws of physics and the universe. So, just to recapitulate, dark matter is this presence of much, much larger gravitational energy that can be sent throughout the universe to like a much larger degree than actual matter. And I think dark matter represents about 27% of the energy in the universe.
Okay.
Dark energy is what is driving the expansion of the universe itself. If we are in a universe where, because of gravity, because of this like perfect force that brings everything to collide together, you would end up with a scenario where everything just collides into itself and, would combust into this big clump of energy and get smaller and smaller until it reaches singularity again. So that would
Yeah.
be if the universe wasn't expanding.
Okay.
But I'll again go through this when I'm talking about the evolution of the universe. But we have dark energy that is pushing everything away at increasing. So basically, when you're talking about like the size of the universe and how it grows, you have dark energy fighting against matter in the universe, and that includes baryonic matter and dark matter. Baryonic matter being the matter that we see all around us, which composes like 5% of the universe's energy.
Damn.
Sorry?
Only.
Yeah, that's it. Like everything we see around us, like literally everything we can see, everything we can possibly see in the universe through light represents 5% of the energy spectrum of the universe.
Okay. Another dumb question.
Mhm.
Where's the rest? Where is the dark energy?
Well, that's why we call it dark, because we can only see it through its gravitational effect. It doesn't interact with regular matter. It doesn't interact with light. It doesn't come into contact with
But
anything.
it pulls.
But it will curve space-time itself, and it pulls, yes. And we can see this pulling through a couple different ways, mainly through gravitational lensing, which is so gravitational lensing is whenever you're looking at the light coming from a specific object. If the light is passing through a region of space that has really, really high gravitational density, such as like the sun, for example, or like super, super large galaxies, if the light that's traveling through space passes by these regions, it'll literally curve. Like the direction the light will take is going to curve according to this gravitational pull.
Wow.
And we can monitor this and model this and then see the effects of how much the light is getting bent by when it's passing through these regions of space. And it's getting bent in places that we don't see any matter, baryonic matter. So there must be something else contributing to the gravitational lensing of the light. And the only explanation is if dark matter exists. That's one way. Another way is also by looking at how galaxies and stars clump together.
Mm-hmm.
There is visibly not enough matter for a lot of galaxies to even form in the first place, but they end up forming anyway, which means that there must be some sort of like dark matter that contributes to an increased gravitational pull, bringing all these structures of the universe together.
Okay.
Well, that's mainly how we can detect. There are a few other a little more involved ways, but that's kind of the basis of it.
Okay. So far, so good.
Yeah. A really cool way, actually, like talking about like gravitational like lensing, the way we can see these like gravitational fields is quite nice. You use lasers, and then the laser you're reflecting the light that you get onto a mirror, and then the mirror will literally deform itself when a gravitational wave is passing through it, and the laser will track the movement because it's like super precise, and we can know the effect of the gravitational wave that way.
Oh, wow.
And this is all very like new technology. There's like LIGO, which is like the main laser, like I think it's like laser interferometer geo something. Basically, they're the ones who do like a lot of the very heavy duty astronomical research of the universe.
Mm-hmm.
Yeah, so that was just like side note.
Okay.
But yeah, then I hope that answers the question.
Yeah, it opened a bunch more, but yeah.
Okay, so where was it? So that's
Microwave.
I guess that fully covers like redshifting, right? And that brings us to how Big Bang was coined in the first place. I think this is kind of like a funny tidbit, but in 1949, Fred Hoyle, who was just like some random astronomer, not so random actually. He was the one. He was like I think the one who like mainly contributed or was like one of the founding researchers on how elements are synthesized in stars. So like the production of hydrogen, helium, and lithium, etc. How they form in stars. He was like a pioneer of that kind of research. Which is cool. And he was making fun of Lemaitr's idea that there was an origin to the universe and that it created everything out of nothing. And he called it in a joking way the Big Bang. I'm like making fun of him.
And that stuck.
And that just stuck. Yeah, like that was, I think he was getting interviewed and then he like kind of made fun of the idea, and that's kind of what astronomers and cosmologists call it ever since. So now, the main thing that proved that the Big Bang is indeed what actually happened is that you end up with the cosmic microwave background, the CMB,
Yes.
being discovered in 1965. So this is like a really big moment for our current model of the universe because it quite literally offers a snapshot of what the universe looked like just shortly after. When I say shortly, I mean on the scale of like a couple 100,000 years, but just shortly after the Big Bang. And it gave us a visual picture of what the universe looked like back then. And we can trace back what our current universe looks like to this snapshot and tell from this how it evolved.
Okay, so what is the cosmic microwave?
So it is, I guess I can first talk about how it was found in the first place. So at Bell Labs, which is like a laboratory that honestly contributed to a lot of like physics research during the 20th century, also slightly problematic lab in terms of like women's rights and ethics and,
Ooh.
you know, EDI. That's besides the point. Bell Labs is super cool for this part of the talk.
Yeah, we'll just gloss over the sexism shit.
Yeah, exactly. That's fine.
We don't care about
So they
sexism.
found faint radio signals coming from all parts of space. They built this like radio receiver. They wanted to see if they
Aliens.
can. That's what I thought originally, but they just wanted to see if they can receive radio waves from other parts of space. They were scanning like places within our solar system, a little bit further beyond, even within our galaxy or beyond our galaxy. They were trying to see if there was some sort of like celestial entity that exists in regions of space. What they end up finding is that they see this like kind of faint radio emission coming from all parts of space at the same frequency. It is the same. The term they use is that there's no anisotropies,
What is
where an
that?
anisotropy is a, like, let's say you're making a map of space. Any region that isn't constant in density, that's like an anisotropy. So it's regions of space that are like non-constant. They're changing.
Okay. You
So
said
for
this was during
example,
the
like if you're
70s that they were doing this? Sorry.
so sorry.
You said this was during the 70s they were doing this? Like detect like just trying to get signals from
This is 1965. Yeah.
I was gonna
Okay.
say,
So
I
they're trying.
remember, it's just gonna be a little side note here.
Yeah, that's okay.
Because I remember reading something about this at some point, how like in the 70s they were just like picking up signals from space and they got the WOW signal. I don't know if you know.
No, I don't.
It was just like a radio burst that
Okay.
they detected at some point from like a constellation, and it lasted like a little bit over a minute, and
Oh, I
it
think
was
I
never
did hear about this.
repeated again, and it was just like very unique signal, and they
Mhm.
don't know what the source was, and so I think one of the scientists wrote on it just like wow, and then they called it like the
Wow.
wow signal. Yeah.
Interesting.
But yeah, okay. Anyways, so I just thought it was interesting. And then people thought it was aliens, and then some people thought it was like just like different celestial bodies clashing or whatever.
Yeah, yeah, yeah. It very well could have been. A lot of the radio waves we get are from these kind of like nuclear reactions, nuclear explosions. You can have gamma rays, you can have stars colliding or black holes colliding, and they'll release radiation throughout the universe.
I like to call it the Owen Wilson signal. Wow. Right,
It's
continue. Sorry for
quite a
interrupting.
fitting name. Yeah, so the people that built this at Bell Labs was Arno Penzias and Robert Wilson. They were awarded the Nobel Prize in 1978 for their discovery of the CMB.
Okay.
And again, it basically gives us like a snapshot of the early universe around 380,000 years after the Big Bang. And this is kind of one evidence of the Big Bang and the expansion of the universe. Another evidence is that matter on a universal scale is very evenly distributed. So even though there's like star clusters and galaxies that are formed like throughout space, on a large scale, matter is distributed exactly as it is in the CMB. Like the way matter is distributed across the universe now has the same like anisotropies, so inconsistencies in like density, to how it was back then, just on a larger scale. So that's why we say it's
So
sorry.
we had a snapshot of the universe, like relatively shortly after the Big Bang.
Yeah, like 14 billion years ago. And
And
matter was organized in the same way that it is
same way,
now.
but just now it's more spread out. And how exactly does the microwave give us a snapshot of the?
Because that is when light from the Big Bang, so at the beginning, it's the first light that escapes after the Big Bang happens.
Yeah.
I'll go into a little more detail of like the dark ages right after the Big Bang and stuff like that. But for now, all you have to know is that light escaped about 400,000 years after the Big Bang.
Okay.
And this light just reached us, as we're observing it. And we see it to be. This is kind of the outer limit of the observable universe, is this cosmic microwave background. That's the furthest light we can see.
Yeah, okay. Okay, now I understand.
So if you think that we're in this kind of like reversed, like inverse sphere, on the edge of this surface of the sphere, like I guess inner surface, you'll have the cosmic microwave background being overlaid, and we're kind of like in the middle there, right? So they find this CMB, and as they proved it in 1965, and even like many years later, we come to the conclusion that matter is evenly distributed across the universe. Very nice. And through even more recent findings, I think like in 2013, the Planck Space Observatory, they completed like a four-year scan of the CMB radiation. This kind of like recent data shows us that the universe is getting even more and more uniformly distributed than we even thought previously. So
as
high
it's
confidence
expanding,
there.
it's also
No,
becoming more
it's just
uniformly
as
distributed.
we're getting more precise with our instrumentation, we're seeing it as being actually more
Okay.
uniformly
Than we
distributed.
first thought.
Hence, yeah, and hence this theory is getting more and more proven, like year by year, pretty much.
Okay.
Yeah. Okay. So that's kind of the background you need to know. And now I was going to go over like the different evolutionary periods that stem from the Big Bang. So we'll take it trillionth of a second by trillionth of a second to start. So
That's
at
the
about 0 to the negative 32 seconds, that's 0.0 times 32, 1,
Okay.
inflation starts. So this is kind of the first part. You have the Big Bang and then you have inflation. The Big Bang is basically the presence of matter entering a enclosed system, and this enclosed system begins inflating very rapidly at the beginning. So you have this like hugely exponential inflation. If ever you've seen like images, visual depictions of the evolution of the universe, you see it's in the form of like a shuttlecock.
Yeah.
Like
Where
badminton?
yeah, exactly, where like the tip of the shuttlecock is origin Big Bang and then inflation, and then it kind of just like linearly grows outward like that. That's kind of how you have to picture the universe growth.
Okay.
So if inflation didn't happen, the reason why theoretically it's sound, even though we can't necessarily prove it, is that just the fact that the universe exists today, we wouldn't be able to exist if inflation didn't occur. So it's kind of like a reverse logic where because we're here, it only makes sense that we got here if this happened, even though we can't necessarily prove that this happened.
It couldn't have like
Very
slowly
specifically.
grown?
It's like the most logical
No.
explanation. It's like the most.
Yeah, because there's so much matter and energy at this kind of beginning, at this creation, because of the amount of matter that exists in the universe today, it should have just collapsed in on itself within any given space. But because for some reason inflation happens, it was allowed to, like, the density of the universe got small enough that the universe was allowed to continue to expand. So at first you have this like huge expansion. Okay, everything grows to like an enormous scale. And then slowly, as the matter starts to form, as the universe gets denser, the gravitational pull from all this matter is starting to bring the universe back down. So it's at the beginning, expansion. After that, you have slow decrease in size.
Okay.
So 1 microsecond after the Big Bang, you have the first particles that appear. So when I say particle, you have this like hot, dense soup of neutrons, protons, and electrons.
Mm-hmm.
And you don't have elements yet, but these very elementary particles start to form. Then 3 minutes after the Big Bang, the first elements start to form. So you have hydrogen and helium being the first two, and then lithium. So this is all the same elements that are also found in the sun in like abundance.
Okay.
So stars, they are basically like nuclear reactors themselves, and their factory, they're using the same elements that started the universe in their cores, right now actively.
Mm-hmm.
Yeah. Then this is where a lot of time passes by. These elements start to get like heavier and heavier as the universe is like slowly growing, but the expansion rate is slowing down. Still growing, and the total volume of the universe is growing, so the energy density is decreasing. And so you have the universe gradually cooling down. And because the universe is cooling down enough, you have denser and denser particles that are able to form. And once the universe reaches a sweet spot, around 380,000 years after the Big Bang, you have a universe that the photons that were present in this kind of like soup of particles, something to know about photons is that in their environment, they are less and less energetically, like they have less and less energy based off of their temperature.
Okay.
So light, for example, if light is coming to you from at a certain temperature, it'll have a certain amount of energy that is accompanied with it. And these photons now at this point of the universe, 380,000 years, they don't have enough energy to be knocking off electrons from atoms, and molecules are able to form. Because before that, you have this kind of constant mess where like nuclei are formed. So you have like protons and neutrons that exist, and then they're trying to attract electrons. But as soon as they attract an electron, a photon comes in and knocks it right out, kind of like like a bunch of soccer balls being kicked around. Some sort of analogy for comprehension. It's not at all what's going on.
So
But
there was no light for the first 400,000 years.
there were photons, but the universe was like an opaque kind of cloud. So this is what's pre 300,000 years, 380,000 years. You have what's known as the Dark Ages. Or sorry, Dark Ages come after that. But at first you have this like fog. So this fog means that the universe is like really opaque because you don't have heavy elements that are forming, and it's just kind of this like soup of particles. Then the universe cools down enough where light doesn't have enough energy, the molecules form, and then light escapes from these interactions. So they're not colliding with like electrons anymore, they just pass right through because the universe now, from being this like big fog, is transparent.
Okay.
And that light that escaped at that very specific moment when the universe went from being this fog to being transparent, that's the CMB.
I see. Okay. Yeah. It's all full circle now.
Yes.
The CMB that
exactly.
we're seeing is the light that the first bit of light to escape.
Exactly. That is exactly it.
So is that what we see when we look as far as we possibly can?
Yeah, that's the outer limit of the observable universe is the CMB.
Okay. Okay. So do you want to kind of explain what the observable universe is?
So the observable universe is everything that we can see through light of the universe that is enclosed within the furthest light
But
being the
so I
CMB.
guess it would be easier to explain what is the unobservable universe? Or
That's
why is there
anything
even a part of the universe that we can't see?
because, okay, so the universe, if you think about it, as it expanded, so the light that we're seeing of the CMB, that's the light that took 14 or 13.75 to be exact, 13.75 billion years to reach us.
Yeah.
And that is the limit of what we can see in terms of observable universe. So anything that's enclosed within this space, anything that emitted light that traveled for 14 years or less, we can see. Anything beyond that, if the universe actually expanded to like a lot more than we imagined, beyond the limits of the speed of light, that we're unsure of.
But so do we is the consensus that the universe is expanding faster than light?
The consensus is that the further, and so you know how I was talking about redshifting?
Yes.
So another nifty thing about redshifting is that based off of the redshift, you can tell how fast a galaxy is receding from you.
Okay.
And based off of redshift, this is where kind of the laws of physics seem to break down. Some galaxies appear to be moving like faster than the speed of light away from us.
Whoa.
The reason for that, you'd have to like look at special relativity a little bit and the movement of speeds of different things in relation to the speed of light. But how should I
So
say
light is
this
not the
without?
fastest thing in the universe.
It is. Light is what's very important to take note of is that things that we measure to be moving at faster than the speed of light does is not an inertial state. And the concept that the speed of light is the fastest thing in the universe is that at inertial points, speed of light is the upper limit of the universe. Like nothing can travel at that speed,
Okay.
not even space itself. But based off of the redshifting, based off of the way the universe is expanding with the light that's coming towards us, also taking longer to get to us, our impression of this speed at which it's moving away is like it approaches infinity. Like it just gets larger and larger. Even though in its like local region, it's not moving, it's not expanding at faster than the speed of light. It's our impression of it.
Okay.
I don't know if you've ever heard of like the theory of like the twins on like an airplane or
No.
on a rocket ship,
Nope.
where like one twin stays on Earth and then the other one is in a rocket ship traveling further away and then comes back and he's traveling at like a certain ratio of the speed of light. And so Einstein came up with these equations of special relativity based off of like Maxwell's equations that depict that time moves differently for the person on the rocket ship than it does for the person on Earth. And for the person that's on the rocket ship, because they're moving at a certain speed that's in proportion to the speed of light, let's say like 0.5 times the speed of light, time for them passes slower than it does for inertial observer person on Earth. So if one twin is on a rocket ship moving at half the speed of light and then comes back to Earth, they'll have aged less than the person who's been on Earth.
Wow.
Yeah,
Wow.
and because like time, if time is can dilate and is part of space time, like your biological clock is also a clock, and you age according to the laws of physics that you're under.
So is this a possible key to like immortality?
It's perceived immortality because you're gonna see like the same amount of time pass. Like if you're on a rocket ship moving at like super high speeds, like in your rocket ship, you don't see time move any differently. You're gonna live like 100 human years and
Like you're not
whatever.
living longer, it's just that
It
time
just
for
feels
everybody
like you've
else
lived.
is like passing at a different rate.
Yeah, but everyone that's still on Earth,
You know that happened in Interstellar, like that whole thing of like
I think,
he
yeah,
goes
yeah,
into a
yeah, it does.
wormhole and then
That's
I actually haven't
incredible.
watched that movie. Maybe I should.
Hmm.
That's incredible.
Yeah,
So
that's
that's
crazy.
based off of this is how I can kind of loosely relate to the concept that things are appearing to move faster than the speed of light, even though in their local region they're not. It's just because they're so far away, we get this like increased shift.
I see. But
But
so
in every local region of space, space expands at the same rate.
which is the lambda?
Yeah,
Okay. Okay, see I'm getting somewhere.
yeah. No, you're good.
Okay.
Yeah.
So
So you
where are
have
we now?
this is we just passed the recombination era. So recombination is where electrons are able to bind to atoms, so protons and
So are we
neutrons form
getting molecules
molecules.
now?
Sorry,
Are we getting molecules now?
this is where we get molecules.
Fuck yeah, bro.
So it's called the recombination. I don't know if this is like pertinent, but in like nuclear physics, you're talking when you talk about something being ionized, it's that you're sending typically like a photon or light or a laser, and you're knocking off like an electron or adding an electron to a element. And so this is the process of like ionization, and then recombination is the opposite of that. So
Combination.
bringing things back together. So before we have
Okay.
photons scattering electrons, and vice versa, and obviously the photons being scattered themselves. But then now we have recombination, so electrons are now bound to their atom, to their nucleus.
Okay.
And then it takes millions of years. So we go from 380,000 years to 200 million years before the first stars are formed.
So this is the dark age.
So up until the first stars, that's the dark ages of the universe. So all these elements don't actually produce light. You need stars to start emitting photons themselves. So until the first stars, which happened at around 200 million years according to NASA.
So at this point, light was a thing, but it was just no source of light. So we were all in the dark.
The only light was the CMB light until this point.
And how bright is it? Would I be able to see it with my eyes?
No.
So okay, so
Well, can you see the light of it's literally like the furthest point of the universe.
Yeah, but if you were there.
Like you can't see it with the naked eye.
No, but what if you were there?
Oh, yeah, of course. It is light. It is light that comes from this like energetic soup.
Okay, yes. No, that's all I was wondering. I know I can't see it from
Yeah.
But-
Photons are photons. They behave in the same way. But these are like, we call them like relic photons because they're like the oldest photons
They
that you
have
have.
so much aura, bro. I don't know how you're feeling, Parsa. The fucking
Dude, the
microwave.
name, the nomenclature for these things are just
They're
like
the first source of light. They're the light that escaped the Big Bang. That's incredible.
Yeah, it's amazing.
some crazy
But
lore.
what produced those photons? I guess I missed the part.
Well,
but-
all these particles are created at the time of the Big Bang. There's a bunch of particles that I
Okay, but
haven't
this is
named.
okay.
Like,
But
all I
there's the
talked
ones that
about was
escaped.
protons. Yeah. There's other particles that did escape, and these, again, this is going a little more into like specifics that we call neutrinos. These are particles that don't interact with matter normally, for the most part, and which means they can just kind of like pass through things.
Mm-hmm.
But they do interact on the scale of the weak force. So if you remember, I talked about like the
Yeah.
4 forces of the universe. So you have the strong force, the weak force, gravity, electromagnetic force. The weak force is tied to the neutrinos. And these escaped like right after the Big Bang, I think within a few magnitudes smaller than 1 second seconds. And they contributed, according to certain theories, to the anisotropies, the way that matter condensed in certain regions of space, because they created some sort of like imbalance. Because if the universe had like perfect like energy density, we wouldn't have like stars forming or like black holes or galaxies or clusters of anything. Like everything would be spread out like so evenly that we wouldn't have this kind of like cluster of things. But because something happened at the beginning to create these small pockets of irregularity through like gravitational effects, that made it so that we have our kind of universe that produced these clumps of matter.
Okay.
Yeah, so anyways, tangent on that, but neutrinos, super cool to look into. Very interesting stuff. And then so after 200 million years, you have the first stars, gas and dust condense into stars.
Finally.
Then you get 400 million years, and after 400 million years, you get galaxies and dark matter forms. And then not much happens for about 10 billion years.
Are there any stars from that time that are still alive?
Yeah. Well, from that time, like
Yes, from 200 million years after the Big Bang.
I think they're called population 1 stars. Population 1 or
But
I
so
know
they're still around, some of them.
Probably not, because they
Fuck.
would have. We can see them as they were back then.
Oh yes, it's true because they're so
Yeah.
far.
Yeah, exactly. We see them as they
Okay,
were
but if
back
you like
then, but
TP
right
there,
now
it would be dead.
they've probably already exploded. Yes. Bless you.
That's you.
And then you get to 10 billion years. So like
Okay,
you
well,
know,
whoa, I feel like I kind of
9.5
skipped.
billion years. Yeah, 9.5 billion years after galaxies and dark matter, you have dark energy. So you remember how I said like first you have the inflation, then you have the universe is expanding, but the expansion is slowly receding.
Yes.
And then for some reason, we don't know why, but after 10 billion years, it starts to expand increasingly again. So the rate of expansion now accelerates, and we attribute this to dark energy because there's no other explanation as to why things now start getting more and more separate from each other. Which leads to today, 13.75 billion years later, and we're talking about this evolution.
Wow.
So that's the big picture.
Okay. Holy shit. Any questions, Parsa?
My brain is numb. It's become mush. No, do you have any questions? I didn't think of it at the moment. Well,
Okay, I have a
feel like-
question for you. Sorry, okay, go ahead.
No, I guess I did want to ask if there are like, we're talking about how the universe started. If there's like alternative, theories to it, or if there's theories as to how the universe will end.
The theories of how the universe will end, I will definitely get into. Other ways the universe started, do you mean like before the Big Bang? Other
Other
um
theories, I guess, more
other
scientific
theories than the Big Bang?
rather than like religious or philosophical.
Not any like serious ones. Like the Big Bang is the most generally accepted and mathematically sound theory.
When you say not serious ones, like what do you mean by not serious? Like
Like
anything.
to think that like if you choose to like literally not believe in the science that we have today and be like, oh well, the universe always existed or some shit like that.
That's like the atheist.
Yeah,
The OG atheist.
The
OG
OG
atheist.
atheist, not the new age atheists.
No, no, fuck them.
Well,
Okay, so 1 billion year galaxies appear.
Galaxies appeared at 400 million years.
Okay,
the scale at which like we are
10 billion years is where dark energy comes into play,
which is when the universe started expanding much faster.
yeah.
and where it started expanding at an increasing rate for the first time.
How can it appear after 10 billion years?
Oh, that's why we call it dark energy. We literally have no way to explain it, and so we say it's this like invisible energy pushing things away at a stronger rate than gravity pulls things together.
So we
These
don't
are
know
all
shit about
estimates
dark
though,
energy.
right? Like when we're saying
No,
10
no, this
billion
is
years ago.
observed.
But like when we're saying 10
The
billion years
estimates for
ago,
timeline
yeah, the
is
timeline. Like how are we even measuring such a thing?
that's all done through like this is where you say, "Trust me, bro."
Yeah, legit shit, Parsa, like shit you and I wouldn't even understand.
Yeah, but like are they like doing tests with
Like
it with like
how like
those
yes, how confident they are, pretty significant degree. According to our model, this is the math that works and the math that describes our current universe. So if you're subbing t for time in one equation, you end up with other parameters, and so that's how you get like how we're going back in time and studying these things. The very helpful tool is the CMB because it provides a snapshot of all the parts of the universe that existed very early on, and we can apply our current model to what it was back then and see that the laws of physics still work. So we can fill in the gaps in between.
Okay, let me ask you this. You said we know what happened after 0.00001 second after the Big Bang, right?
Add so many more zeros to that, but yeah.
Why can't we see, right before that?
Because
Like, why can't we see moment zero?
because we don't have a model that explains why there is even matter in the first place. Like the main thing to figure out is
what started the
Why
Big
is there
Bang?
something and not nothing?
Like why was there even
exactly
a Big Bang in the first place?
because like purely theoretically and mathematically, like matter and then its like evil twin antimatter would just come into existence and collide and form energy and dissipate and come to existence and form energy
Right.
and collide. This would be a repeating cycle, but for some
For
reason,
eternity.
yeah, for eternity. But for some reason, matter dominated over its like counterpart,
Let's
and then we
fucking
ended
go!
up with a universe that's full of matter that we see around us.
But we still don't know why. We don't know how matter like
We
won
don't
out.
know why.
So
No,
what
we
do you mean
know
by
that the
like dominated
probability
over
of
its
that.
counterpart? Like was there a risk or even like an alternative where antimatter dominates over matter?
That there's alternative theories where there's other universes that exist that are antimatter universes, and that the laws of physics
What?
are literally inverted.
What?
What? So you would
Yeah.
like gravity would be reversed and you like back away from.
An electron would be positively charged and a proton would be negatively charged.
What? So
When
like
you
the
say there's
laws of physics would be inverted or just like
And like well like the yeah like
gravity would
everything that we know
fluctuate?
about matter and antimatter like would be the opposite. So you'd have like a particle, like a proton, that is negatively charged, but now has the mass of a proton. But then you have an electron that is positively charged, but has the mass of an electron, and that changes the physics completely of how they
I
even
can't even
interact.
imagine what that would look like or behave like or just like
No, well, we can't. Yeah, like we
that's
literally, it's like reinventing the rules of physics and like trying to figure it out, you know. But that's a
that's
simulation for
crazy.
another day.
Holy fuck. Okay.
So yeah, we can't see at the zero mark. That's kind of like the holy grail of like astrophysics study is
Marco
like
figured
getting
it
to
out,
that
yeah.
Is
bottom
it
point.
is it
And that's
possible?
when you get into like philosophical kind of debates about what happened and yada yada yada. But yeah, is it possible?
I mean, I feel like
Unless we can
Tristan knew it
create
was.
and own version of a Big Bang and have like a controllable variable that allows us to do it in a way that's reproducible and that we can understand, that would be the only way I think that we can figure it out.
But aren't we creating mini Big Bangs?
So you may be wondering that I've said that the CMB escaped 380,000 years ago, right? But how do we know about everything leading up to that point? Because universe should have not had any light, and so how would we,
Yeah.
we can see a snapshot of 380,000 years after Big Bang. How do we know about the original stuff? So a lot of this is found using like mathematical models and predictions of like our current nuclear theory. So one of the main ways to do it is by using particle accelerators to create these kind of like mini Big Bang environments, which is essentially we're shooting neutrons at particles and we're getting this energy. And this is like mimicking how a Big Bang would have occurred in the first place without the inflation stage, which is the reason why our universe became like stable and existed.
Yeah.
And so through these like mini Big Bangs that we're creating in, for example, like the Large Hadron Collider in Switzerland,
Mm-hmm.
a lot of what they do is research around that. And you can build mathematical models based on what's happening and then see if this model, if you were to expand it to the scale of our universe today, if it fits. And then we find that it actually does fit. So an example is like by creating these environments, Big Bang environments, you're recreating like the soup of the universe that existed. And then from there, you get an approximate like 75% hydrogen, 25% helium, a little bit of lithium that originate from this kind of interaction. And that is exactly what we see in like the formation of stars, for example.
Okay.
Or if we're looking at like super old like gas clouds that exist in the universe, we see that they're composed exactly of this proportion of elements. So we see that like if at the origin these are the elements that get created to this ratio, and then we expand it and see that like way later on in time this same proportion is kept, it must be that these environments that we're creating are akin to what would like to what the Big Bang would have been,
Okay.
if that makes
Wow.
any sense.
No, totally. That's incredible. It's great, bro. Humans are so sick.
Yeah. Another way to prove it is like kind of the gravitational footprint that neutrinos had made, which I talked a little bit about earlier. So the neutrinos escaped like a lot faster. They escaped within like the first trillionth of a second.
Okay, like before matter.
No, neutrinos are still technically matter.
But like what? What the fuck is a
They
neutrino?
just don't interact. Sorry?
What's a neutrino?
I will not get into that.
Okay, fair enough.
All you really need to
Totally
know
respect it.
All you really need to know is that it's a particle with almost zero mass, with no charge, and almost doesn't interact with regular matter, but it does have an effect. It does come up in nuclear decay. That's where most of it comes up.
Okay.
So when a neutron decays into a proton, it'll typically emit when a neutron undergoes decay, it'll emit a proton, an electron, and a neutrino.
Okay, yes.
Yeah. So that's where neutrinos are typically. And because they escaped, they were not bounded by the same constraints as like photons, which were knocking around into electrons. And so neutrinos escaped really, really quickly and then could have created these gravitational anisotropies within the space that was contained in the universe at the time.
Mm-hmm.
And what could have been the cause to like how galaxies and stars and clusters of matter formed in the first place.
Okay.
So that's fine and well. Now we've shown how we've talked about the CMB, we know about the evolution of the universe, we talked about how we know about the Big Bang, talked about its history as well,
Mhm.
current like cosmological model, the lambda CMD model. So that's fine and well. Now we can talk about like, do you guys have any questions at this point?
I wouldn't even
Not
know
really.
where to begin.
Yeah, me neither.
Is there anything that you wonder about the size of the universe?
I mean, if you mention it.
Well, we were already discussing, though, with the observable universe,
Yes,
but we know how big it currently is.
we know how big it currently is, yeah.
Despite it not
Based
being
off of the path that the light took to get to us,
But okay, how can we
and
know?
looking at based off of how redshifted it is. So right now the CMB light that we see, super turbo redshifted. Based off this redshifting, we can tell how far away it is.
Yeah, but doesn't that measure the observable universe?
Yes, it does.
But so we
But
don't know
so
how
if the
big.
universe is 13.75 billion years old,
Yes.
how big would you expect it to be?
Well, I don't know how fast it grows compared to the speed of light.
Yeah, that's true. Okay. But would you expect it to be less or bigger?
Well, I already got spoiled that it's bigger than the speed of light.
Well, then you should have asked Parsa what he thought.
I don't think Parsa thinks.
Okay, maybe not.
Whoa, I have thoughts.
Sure, buddy. Do you think the universe is smaller or bigger than the speed of light times the universe's age?
Do I think the universe?
Like, do you think the
It's
universe is
bigger.
smaller or bigger than 14 billion light years?
I think it's bigger.
Why?
Like, are we talking end to end?
Yes.
Yeah, end to end. Like,
Why
if the
do I think
universe
that?
is 13.75 billion years old, how would you expect it? How large would you expect it to be if light from the CMB came to us after around about 14 billion years?
I don't know.
Okay, so the answer is about 93 billion light years wide.
How do you know that?
So it's smaller.
93 is smaller than 14?
Can I
Oh,
say that? Can I
14.
please
It was
say the R
I don't know
word?
why I thought 140.
Yes, you
is
can, and
big.
I will
I'm
not cut it.
forgetting things. I'm sorry. I apologize. I'm losing my mind. I'll
But
be
how?
honest.
Okay, Tristan. First, how do we know? It's
So I was right.
What?
Because it's exponential, brother.
No, it does not grow exponentially.
Does it
But
not? I thought it did.
no, it grows at an increasing acceleration, but it's not exponential growth.
Okay, it's
Like
linear.
inflation. Inflation was exponential growth, but now it's accelerating. It's increasing at an accelerating pace, and the acceleration is increasing with time, but in a linear fashion.
Okay. But I feel like you're skipping my question. How do we know how big it is?
So you just measure it end to end with a really long ruler, and that's about it.
Okay, what do you use Parsa's?
What? Get out. Get that shit out.
Get in, bro, please. So
Could we?
enough dodging the question.
Yes.
So based off of the way we like more specifically know this, would be going to like a lot of mathematical detail, but basically it's off of the redshifting. So the redshifting gives us a measure of not only the speed at which something is receding, but also of
Like
what the
Marco's
distance the light would have had.
All right, continue. Apologies.
What distance the light would have had to travel to get to that redshift value. And so it's found that based off of the light redshift, it's about 46.5 billion years away. So if we multiply that by 2 to get the full diameter of the universe, you end up with the full size being 93 billion light years.
Wow. So the cosmic background that we're able to see
Yes.
has already traveled 46.5 billion
Yes.
light years
Yes, exactly.
by its current redshift.
In all directions.
That's incredible.
Yes.
So there's a lot more universe that we'll never be able to see than what we'll be able to see.
Yeah, that's for sure. And then like there's some other like cool facts. So at the point at which we're seeing the CMB, so like about 46 billion light years now away, that distance, if I'm not mistaken, this is just like off the top of my head, originally would have only been about 500 million light years, if I'm not mistaken. So in a stationary universe, it would have taken about 500 million. Well, yeah, but like 500 million compared to 46 bill.
Yeah, that's true.
Yeah.
You know.
What the fuck?
Yeah, so the light took from 500 million years to 14 billion years to reach us due to expansion. Kind of nuts. And
Yeah.
also, right now, because the universe is expanding at like an increasing rate, and if it continues to do so, that would mean that anything which is within the vicinity of about 15 billion light years radius, so if the whole universe right now is 93 billion light years in diameter, so 46 billion year radius, only about 1/3 of that radius will ever be able to actually see as it is right now.
What?
As the space expands and things grow farther and farther away. And when I say we, I mean like Earth itself. If
Yeah.
Earth were to continue, living on for forever, the furthest light we can see as it is today is about 15 billion light years away. Because by the time it
Yeah.
takes to get to us, like the universe will have expanded so much that we can't get any light coming from further than.
That is insane.
Yeah. So pretty nuts.
Wow.
That leads me to asking you what could have happened before the Big Bang.